Okay. Okay, so let us start. You can hear me, right? Okay.
Yes.
So this is the course on thermal physics. We will be discussing the properties of matter under temperature, under different temperatures. So how properties of matter, how matters change, what are the properties, thermal properties of different matters. So that will be the object of this course. And there are three topics we are going to cover. We are going to cover. So first one is thermodynamics. Second, we will discuss phase transition. And third is the kinetic theory of gas. So these are the three topics we will be discussing in this course. So we will start with thermodynamics. So today I will start with thermodynamics and we will discuss thermodynamics. I think it will take I don't know. So I will have 12 3-hour classes. So thermodynamics will take I think 6 to 8 classes. Then I will discuss phase transition and kinetic theory of gases. So today I will start with thermodynamics. So everyone can, this board is visible, right? This part of the board is visible, yes or no?
Yes,
And
sir.
you can hear me.
Yes, sir.
So in thermodynamics, what we discuss, we study the large scale or the gross behavior, gross properties of some system. Okay, so I have already introduced few words which need to be discussed. So I have introduced the word called system. So what is called a system? A thermodynamic system. Okay, so system is anything on which our attention is focused. So I am taking the class in this room and I am working on this board. At this point, this board is a system for me. My focus is concentrated on this board. It could be anything. System always comes with surroundings. Okay, so everything surrounding this board is the surroundings of this board. Let us take another particular example. The simplest one, let us assume that I have a box. I have a box full of gas. So this is my system. This is my system and everything surrounding this box is the surroundings of this box. The objective of thermodynamics is to study the properties of this gas and its interaction and of this gas on which we are interested in and its interaction with the surroundings. So what we will be trying to study the properties of the system as well as we will also study its interaction with surroundings. So this is the objective of thermodynamics. We will study the properties of the system. Of course, we will study the thermodynamic properties of the system. I will come to that. What is thermodynamic properties? So we will study properties which will be of course thermodynamic. To study the thermodynamics of properties of this system and also the thermodynamic interaction of the system with its surroundings. So surrounding is important because we cannot, ideally it is not possible to separate a particular portion of space. So system is a particular region of space on which our attention is focused. We want to study a particular region of space, so we cannot separate the particular region of space from its surroundings. It is not possible. It is not always, ideally you can have some isolated system, but there will be some influence of surroundings. You cannot realistically separate a particular portion of space from its surroundings completely. So surroundings is the important part. So you need to study the behavior of a system with its surroundings, also study the property of the system. So this will be our objective. So properties, we will study properties of a thermodynamic system. So how can we characterize the properties of a system? What are the variables that we can introduce to study the system? So, how can we describe a system? Okay, so there are two possible ways you can describe a system. You can give a macroscopic description of a system or a microscopic description of a system. So these are important. So there are two possible ways you can describe the system. It could be a macroscopic description. हाँ बोलो हाँ बोलो हाँ बोलो बोलो तो तूने बात किया मिस्टर से तो तुम हॉस्टल में जाओगे ना अच्छा ठीक है तुम कब तक डिस्चार्ज होगे मैं अभी एक्चुअली क्लास में क्लास ले रहा हूँ तुमसे मैं थोड़ा बाद में बात करता हूँ ठीक है Okay, so the description of the system could be macroscopic description or it could be a microscopic description. So what do I mean by macroscopic and microscopic description? So we need to be very carefully define these quantities. What is the macroscopic description for a system and what is the microscopic description for a system? Thermodynamics will be interested on the macroscopic description of the system. Macroscopic description comes from your naive intuition. Okay, so if I have a, say let us consider a specific system. If I have a container full of gases. So this is a container of gases. Okay, so what are the properties of this system? I need to know. What are the variables of this system? I need to know in order to specify the system at a large scale level or at a gross level. So first of all, you understand that since this container contains gases, several gases, so first quantity I want to know is the composition of these gases. Okay, so composition. Say second quantity, what I am interested in is the volume. Obviously, this will be a parameter to specify this particular system. What is the volume of this container? Third, since this is a system of gases, these gases will have some pressure. They will put some force on the wall of this container. So I wanted to know what is the pressure. And finally, I wanted to know this container is hot or cold. So how hot? Hot. Cold. So these are the things I am interested at a macroscopic level on this container of gases. Okay, so I want to know its composition. What are the gases in there? How much fraction of the gases are there in this container? What is the volume? What is the pressure? And whether it is a very hot cylinder, hot container of gases, or this is a cold container. So these are the properties which I am interested to know, and you can assume, you can imagine that this comes from my intuition, right? So all these properties, I mean, if you think that these are the gross level characteristics on which you are interested, so this will come from your intuition, and these properties are fairly easily measurable. Okay, so you can measure the composition by some chemical reaction, and you can study what are the composition of these gases. You can measure the volume since it's a well-defined container, a regular container, so volume measurement is not difficult. You can also measure the pressure by measuring the pressure, by measuring the force exerted on these walls of this cylinder, walls of this container, and you can also try to measure whether this is a hot container or a cold container. So there are few properties which describes macroscopically a particular system. These are few in numbers and easily measurable. So this is the macroscopic description of the system. So this is what we call a macroscopic description of the system, and the properties, I mean, these macroscopic descriptions or the thermodynamic descriptions so these are also called thermodynamic coordinates. Number one, there are few in number. Number two, easily measurable. And number three, they directly comes from our intuition. So this is the properties. This will be, the number of parameters will be few. They will be easily measurable, and we can intuitively find out what are the important parameters that could govern the thermodynamic properties of the system. So this is one kind of description, macroscopic description. In this course, in this course we will be focusing on this macroscopic description or thermodynamic description of the system, and the parameters and the variables which describes a system at macroscopic level, we will call them as thermodynamic coordinates. Okay, so this is the macroscopic description. Now comes the microscopic description. We will not focus on this description in this course, but we need to understand what are the macroscopic description and what is the difference between macroscopic and microscopic description. So microscopic description defines a system at a deeper level. Okay, so let us assume that we take this particular system, a container of gases, different gases. So microscopic description will ask the question like this. Microscopic description will ask how many gas molecules are there in this container. Okay, and what are the generalized coordinates of this gas molecules? What are the, at a given instant of time, what are the coordinates and momentums of each gas molecules? These are the microscopic description of the system. So number of particles, position, and momentum of particle at a given time. Okay, so these are the questions we are asking if we want to describe the system at microscopic level. So how many number of particles we have, what are the positions and momentum of each particle at a given time. At a given time, because the position, I mean, since this is the gases, they are moving inside this container, so the positions and momentums are changing. Their position is changing because they are moving inside this container. Their momentum is changing because they are colliding with other molecules, other particles, and colliding with the walls of this container. So that will change their momentum. So this is the question you are asking if you want to describe the system at a microscopic level. And obviously you understand that these questions, I mean these questions we cannot answer, we cannot measure actually. So if you are asking these questions, if you are describing the system by number of particles and the exact position and momentum of each particle at a given instant of time, given instance of time, so you understand that this question, I mean possibly you cannot answer. Because you cannot measure how many, I mean, it's a container of gases. There are different gases and large number of particles are there inside this container. So precisely you do not know how many particles are there. We cannot measure. That is, I mean, measurement is different. We cannot measure the position and momentum of each particle at a given time. So macroscopic variables, they are in general not measurable. Okay. But we can give some statistical understanding about the system. We can get some statistical understanding about the system from these microscopic variables. I think you will learn this. You will learn this in your. I think in next semester you will have some course on statistical mechanics. There you will learn how this microscopic variable will give you a macroscopic description of the system. How you can go from here to here. So if you do some statistical analysis, you will be able to use this macroscopic variable in order to get some idea about the thermodynamic or microscopic behavior of the system. So we will not discuss microscopic variable, microscopic description of the system here. We will be concentrating on the macroscopic description of the system. So, anyone has any? If anyone have any questions, then you can ask. Okay. So, macroscopic variables of a thermodynamic system are measurable quantity which are necessary to explain a gross behavior or gross dynamics or large scale dynamics of the system. So these are the macroscopic variables usually measurable, and all the time they are measurable quantity. We measure them and we try to use those measurements to describe the system and then predict the future behavior of the system. So that will be the objective of thermodynamics. You have a system, you measure some variables, you formulate some law to derive what will be the future behavior, to predict what will be the future behavior of the system. So this is what we do in thermodynamics. The next important thing in thermodynamics is the idea of equilibrium. Okay, so what do we mean by equilibrium? See, I mean, you all know of all these things, but it is important to formalize things because we are doing physics. So this is important to formalize. What do you mean by exactly? What do you mean by equilibrium in terms of this microscopic and macroscopic variables? Okay. So anyone have any questions? No, right? So let us proceed. example. What do you mean by equilibrium? I will give you two examples regarding this equilibrium and non-equilibrium. What we can say for a system which is in equilibrium and what we can't say for a system which is not in equilibrium. Okay, so let us take a simple example. Let us assume that I have two things. I have two isolated boxes. They are isolated from each other and they are also isolated from the surroundings. Two isolated vacuum boxes. There is no surroundings. I have removed all the surroundings, which is ideally not possible. As I told you that we cannot always, surrounding will always be there. We cannot remove it completely, but for this given example, let us assume that it is possible. Let us assume that we have removed all the surroundings. In one box, I have a jar of solvent. This jar is full of some cold drinks, some solvent. Okay, and in another box, I have a cup of coffee. So these are my two systems. They are isolated from each other and they are also isolated from the surroundings. Now, what will be the macroscopic description of these two systems? So this is a jar of solvent. I can say that the composition will be one of the macroscopic variable. Let us assume that it has, say, for example, 80% of water, the 15% of sugar, and say 5% of lime juice. And it has a volume V and it has a temperature say some T1. So we have not introduced the concept of temperature yet, but you have some idea, you have some intuition about what is hot and what is cold. So let us stay at that intuition and assume that this is the temperature thing. Okay. So this system, it is a bucket full and a cup of coffee. So this system, similar kind of composition I can establish. So let us assume that these are 60% of water, 30% milk, and say 7% sugar and 3% coffee. And it has a volume say V2, this is a volume V1, this is a volume V2, and temperature T. So these systems are isolated from each other and these systems are kept in a vacuum chamber so that they are isolated from the surroundings. Okay, so what I can say that they are in equilibrium because these thermodynamic properties, these microscopic variables for this jar of solvent and for this cup of coffee is not changing. They are fixed. I mean, if we keep this like this, they will remain same. Okay, so when these thermodynamic variables are not changing for these systems, we say that they are in equilibrium. Now, what will happen if I take the jar outside and put the coffee in this jar? What will happen? So since the temperature of this jar, this is the solvent, so this is cold, and this is coffee, so this is hot. Temperatures are different, their compositions are different, their volumes are also different. When I put the coffee from this mug to this jar, what will happen? As soon as I put the coffee from the coffee mug to this jar, this coffee will try to mix with the substance, with the solvent inside the jar. Immediately after putting this coffee into this jar, they will try to mix. We do not have any uniform temperature or uniform composition of this mixture, right? So the upper half will be dominated by coffee, the lower half will be dominated by server, the upper half will be hotter and the lower portion will be colder. So we do not have any uniform temperature. So we call that situation as inequilibrium situation. Okay? So now if I ask that what is the thermodynamic property of the system when the system is not in equilibrium, when the system is in inequilibrium? So the answer is that we cannot give the answer to that because there is no specified thermodynamic property of a system when the system is not in equilibrium. We can only say macroscopic variable, we can only define the macroscopic properties or the thermodynamic variables for a system which is in equilibrium. For an equilibrium system, we cannot do that because there is no uniform temperature for this system, there is no uniform composition of this system. Different part of the system will have different composition, will have different temperature. If we wait for sufficiently longer amount of time, after some sufficiently longer amount of time, the system will come to an equilibrium. At that given instant of time, what we can do, we can tell what is the composition of this mixture. Okay, so we can tell what is the composition of this mixture. It will have some water, some milk, sugar, lime, coffee, etc. Everything will be there, and there will be some uniform composition of this mixture. The volume will be V1 plus V2 surely, and there will be some temperature, which will not be T1, not be T2. In between T1 and T2, there will be some temperature. But we can say we can determine these thermodynamic coordinates when the system is in equilibrium. For an for a system which is not in equilibrium, which is in equilibrium, we cannot determine what are the thermodynamic properties of, what are the macroscopic variable of that system. So you understand. But it is important to note that whether the system is in equilibrium or in inequilibrium, we can always have a microscopic description of the system. Okay, so if I ask the question for this jar when it is not in equilibrium, when it is in equilibrium state, that how many particles are there, what are the particles are there, and what is their position and momentum at a given instant of time. In principle, the answer for those questions exist. Okay, so microscopic description is possible whenever if the system is in equilibrium or not in equilibrium. In both situations, microscopic description for the system is possible, but macroscopic description for a system, for a thermodynamic system, is possible only when the system is in equilibrium. Clear, right? So let us proceed to another more physical example. The example which we'll discuss in this course. Let us assume that this is a cylinder and it has some gas inside it. There is a piston, this is the piston. There is some gas inside it. I put some weight here. Okay, so I put 3 weights here. So this is a cylinder, this is a piston, and I put 3 weights so that the piston gives some pressure on this gas. So there is a gas inside this cylinder. So I can easily calculate. So thermodynamic description of this system. So macroscopic description. So macroscopic description of this system will be the composition of these gases. So let us assume that I have only one particular gas inside the cylinder. So composition doesn't arise. Number 2 will be, so what is the volume? Let us assume that the area of this cylinder is A and this length is L. So simply you can write down this is A times L. So this is the volume, pressure. So let us assume that these weights, each of these weights have a mass of m. So this is the force. Three of them are there. So this is the force acting on this piston. So pressure will be 3 mg by the area of this piston plus the atmospheric. So I put it in this room. So there will be some atmospheric pressure. And it will have some temperature. Okay, so this is the system. This kind of system we will be using frequently to describe different thermodynamical system, gas system. We will introduce this kind of a picture, this kind of a system frequently. So this is a system in equilibrium, because if we observe the system for longer period of time, we will not see that this length is changing, area is already fixed, length is not changing, so that's why volume is fixed. There are three weights here, so the pressure is not changing and the temperature, if it is isolated from the surroundings, if temperature, if it is not in thermal contact with the surroundings, then the temperature cannot change. So the system is in equilibrium. Now what will happen if I remove a weight from here? I suddenly remove a weight from here. So what will happen? So there are three weights. I suddenly remove these weights from here. So there are only two weights. So what will happen? If I remove a weight from here, so this piston will move up because the pressure becomes small, because now the pressure will be 2 mg by A plus atmospheric pressure. So pressure becomes small. So the piston will move up, it will do some oscillation. And during that time, there will be a turbulent motion of this gas molecules inside this system. If I wait sufficiently longer amount of time, I will see that the piston will come to a steady state. Let us assume that L prime, and that L prime will not change after sufficiently longer time. So that will be my volume, new volume. So then the new volume will be L prime times A. The new pressure will be 2 mg by A plus atmospheric pressure. There will be some new temperature. Okay, so this will happen. So if I remove a particular weight from here, the system will go to an inequilibrium state. In that the inequilibrium state means when the piston is fluctuating, when it is coming, it has not came to a stable situation. So that time period, I am calling the system is in equilibrium state. And in that inequilibrium state, we do not have a measured value for L prime because it's oscillating, it's changing, right? So we cannot measure what is the value of L prime. So we cannot say what is the volume of the system because volume is fluctuating, volume is oscillating. So we do not have any macroscopic description for the system when the system undergoes to an equilibrium state. If we wait sufficiently longer amount of time, the piston will settle down at a given L prime. Okay, I can measure that L prime. I have a precise value for this thermodynamic or macroscopic variables. I have a macroscopic description of the system as well as I also have a microscopic description of the system. But when the system undergoes through the equilibrium stages, we do not have macroscopic description, but still we can ask how many particles are there, what are the exact position and momentum of those particles at a given instant of time, and we have a finite time, and we have in principle, we have an answer for that. So microscopic description is always possible, and macroscopic description is always only possible when the system is in equilibrium state. So this is the definition of a thermodynamic of a equilibrium of a system in equilibrium, and we will be only considering the systems which are in equilibrium, because we are doing thermodynamics and we cannot do, I mean, macroscopic description of thermodynamic variables for a system which is not in equilibrium is not possible. So we will only consider systems which are in equilibrium. Okay. So let us go to the next thing, which is the thermal equilibrium. Here we will introduce, I mean, thermal equilibrium is interesting because we are going to do thermal physics. We need to have a very good conception about temperature and heat. So thermal equilibrium actually gives you those things. Okay. Let us assume that we have two systems. System A and these are two simple thermodynamic systems. So as I told you that in order to have a macroscopic description of a system, what we need to know? We need to know the macroscopic variables or the thermodynamic variables for the system. So this could be anything. This could be any number of variables. The number would be few, but it could be 2, it could be 3, it could be 4, whatever. We are taking two simple systems so that the thermodynamic variables, I mean the macroscopic behavior or macroscopic description of the system is possible by two variables. Let us assume that those variables are x and y. So x and y are the macroscopic variables which completely describe the system A. And we have a similar system B, which has macroscopic variables, which is determined by macroscopic variables x prime and y prime. Okay. Now we can take these two systems and place them in contact by two ways. So we can place the system B here or A with macroscopic variables x and y. Separate them by a wall, which we call a diathermic wall. Or okay, so this could be one arrangement. I can separate these two systems by a wall. This wall, let us assume that this is the adiabatic wall. I will describe what is the adiabatic wall later. Or I can place these two systems. Via a diathermic wall. Okay, so what is the adiabatic wall? Adiabatic wall is a separation, is a wall which do not allow any thermal interaction between this system A A and system B. Okay, so this is the definition of adiabatic wall. If I place these two systems in contact with each other via adiabatic wall, what I can say that there is no thermal interaction between these two systems. So you can assume that you have some cold water in a glass and you have some hot water in another glass. You place them in contact with each other through a thick wooden wall. So that wooden wall will act as an adiabatic wall. That will not allow any thermal interaction between two hot and cold objects. Right? So this is the adiabatic wall. And what is the diathermic wall? Diathermic wall is a wall which allows thermal interaction between the system A and system B. Okay, so a similar example, you have some hot metallic block and you have some cold metallic block. You place them together through another metal. So metal is a good conductor, you know that. So they will allow, the metal will allow thermal interaction between these two systems. So this is the definition of a diathermic wall, so that the thermal interaction between A and B occurs. Now what will happen in this case? In this case, the system A and system B are placed in contact with each other through a diathermic wall, so that thermal interaction is not happening between them. So they will not change. They will be in equilibrium. So the system A is in equilibrium state, system B is in its equilibrium state. So they will continue to remain in their respective equilibrium state. Nothing will happen. But in this case, if I place the system A and system B via a diathermic wall, they will interact thermally. Thermal interaction between these two systems will happen, and they will come. They will go through an inequilibrium state because thermal interaction is happening. There is no well-defined x and y for the system A and x prime and y prime for the system B. As long as the thermal interaction between these two systems is happening, as long as they are going through an inequilibrium phase. But if I wait for sufficiently longer amount of time, at some point of time they will come to an equilibrium. Okay, and that equilibrium state we will call they are in thermal equilibrium. So this is the definition of thermal equilibrium. Because we have placed these two systems via diathermic wall, we will allow them to interact thermally, and at some point of time they will come to an equilibrium. That equilibrium is called thermal equilibrium. So this is the definition of thermal equilibrium. Okay, so now comes the zeroth law of thermodynamics. So why zeroth law? Because it has been postulated, obviously it has been postulated after the postulation of first law of thermodynamics. So after the postulation of first law of thermodynamics, people find that there are some more fundamental laws. Something more fundamental than the first law of thermodynamics, which we need to postulate. So they postulate the zeroth law of thermodynamics. So what is the zeroth law? So I'll come to why this zeroth law is very fundamental. Without this zeroth law, we cannot have a conception about temperature. The concept of temperature actually comes from the zeroth law. So I will come to that. So what is the zeroth law? So this is actually very obvious. Intuitively, this law is very obvious, but if we do not postulate this law, we cannot have any conception, any conceptual idea about what is temperature, how to quantify temperature. So I will come to that. What is temperature and how to quantify temperature. So for that, actually, we need to know what is the zeroth law of thermodynamics. So let us take this example. Okay, so I have three systems. I have a system C with thermodynamic coordinate x double prime, y double prime. This is there is an adiabatic wall. there is a diathermic wall. Then I have two systems A and B. This is a particular situation, and let us draw another situation where I have the system C here. I have a diathermic wall here. Then I have an adiabatic wall here. I have system A situated here. And system B is here. Okay, so you can see these two situations. So in this situation one, A and B are in thermal contact, right? So after some point of time, they will achieve thermal equilibrium, but they are not in thermal contact with the system C. Okay, so what I can say that A and B are in thermal equilibrium, but they are not in thermal equilibrium with C. So this is situation one. In situation two, the system A and C are in thermal equilibrium. Okay, because they are separated by this diathermic wall. But system A and B are separated by this adiabatic wall, so they are not in thermal equilibrium. So system A and B are not in thermal equilibrium. But system A and C are separated by this diathermic wall, so they are in thermal equilibrium. And system B and C are also separated by this diathermic wall, so they are in thermal equilibrium. So in situation one, A and B are in thermal equilibrium, but both of them are not in thermal equilibrium with C. In situation 2, the system A and B are not in thermal equilibrium because they are separated by a diathermic wall. But both of them are in thermal equilibrium with C. Okay? So zeroth law of thermodynamics postulates that if system A and B are in thermal equilibrium with the third system C, both of them are thermal equilibrium with the third system C, then system A and system B must be in thermal equilibrium. Okay, so this is the zeroth law of thermodynamics, and since you have the idea of temperature, okay, so you have some idea about, we all have some idea about temperature. This is very obvious to us, right? But imagine that when you do not have any idea about temperature, about heat, when these laws have been postulated, this scenario is not that obvious. You can say that since the A and C are in thermal equilibrium, they have same temperature. B and C are in thermal equilibrium, they have same temperature. So A and B must be in thermal equilibrium. We can say this because we have the idea of temperature, right? But when these laws are postulated, they do not have idea. They are searching for an idea about how to quantify what is hot, what is cold, how to measure, how to quantify the hotness and coldness of different objects. They do not have any idea of temperature. So at that point of time, this is the starting point about the idea of temperature. We will come to that. How this postulate actually gives you the idea of temperature. Okay, so this will be, in this course actually, we will think of simple experiments and try to explain those simple experiments in terms of empirical laws of nature. Okay, so this is the laws of nature, but this comes after experiments. So people have done experiments. They have done different this kind of experiment and saw that A and B are not in thermal equilibrium with C. Then another group of people has done this kind of experiment and saw that A and B are in thermal equilibrium. So these postulates came from experiment because they do not have any idea. When these laws are postulated, we do not have any idea about temperature, thermal equilibrium, etc. So this is the importance of zeroth law of thermodynamics. It might seem very obvious, but this has serious consequences. So let us write down what is the zeroth law of thermodynamics. The zeroth law is two systems in thermal equilibrium with the third must be in thermal equilibrium with one another. So you understand the importance of this law, right? So because this law actually tells you how you can measure the temperature of a given system, right? So this law actually tells you the idea of measuring, idea of comparing the temperature of two different objects. I have one object. I can take some object with close to that object, and I find that the two objects are in thermal equilibrium. Then I can take my object from there and come to another object, and I see that that object is also thermal equilibrium with my object. Then I can say that these two different objects are in thermal equilibrium with one another. So they have something in common. So that thing we know that now we know that that is temperature, but we'll come to the conception of temperature slowly. So this is a very important law to understand what is temperature and how we can measure temperatures. So this is the zeroth law of thermodynamics, and which will give us idea of temperature. I come to that, and then will give us some idea how to measure the temperature. Okay, so let us consider another simple system, another simple setup, simple experimental setup. Some thought experiment. Let us assume that I have three systems. I have a system A with coordinate x and thermodynamic coordinate x and y, which is in contact through a diathermic wall to a system C with coordinate x prime and y prime, which is in diathermic contact to a system B with coordinate x double prime and y prime. So this is my simple setup. I have three systems contact to each other by diathermic walls. So let us focus my attention on these two systems, on system A and system C. Since they are in contact with diathermic interaction, diathermic wall, so they will interact thermally with each other, and this coordinate x, y, and x prime and y prime, they will change. Okay, so they will change because they will interact with each other through thermal interaction. They will thermally interact with the system A and system C will interact among each other thermally. So this coordinate x and y will change. X and y will change. Also x prime and y prime will change. And when the thermal interaction is achieved, the thermal equilibrium is achieved. When the system A and C will achieve a thermal equilibrium, I can specify that particular condition by a function. There will be a function f a b, which will be a function of x, y, and x prime, y prime. Okay, so you understand the point, right? So the thermal equilibrium between system A and system C can be written, can be mathematically ensured or can be mathematically expressed via this kind of a relation. You can I mean, since you know that since you have already have idea about ideal gas system, you can say that the volume pressure and x is the pressure and y is the volume. Here for a system A, this is P, this is B, this is P prime, this is B prime. Then the thermal equilibrium ensures that PV equal to B prime B prime. This kind of a relation. It is true, arbitrarily true for any kind of system. Okay. So this kind of relation will ensure that the system A and C is in this is C. The system A and C is in thermal equilibrium with one another. Clear, right? Now, since the system C and system B are also in thermal contact with each other, they are also in thermal equilibrium. So there must be a different another functional relation which ensures that the system C and system B are in thermal equilibrium. Let us write down that functional relation as CB. This will be functional coordinates x prime, y prime, and x double prime, y double prime. So this function ensures that system A and C are in thermal equilibrium. This relation ensures that system C and system B are in thermal equilibrium. This functional form, this FAC and this FCB, they may be completely different, right? So it depends on what are the system we are considering. We can consider A is a gas system, C is a gas system, and let us assume that B is some solid, some liquid. So then this FAC will be completely different from the functional form of FCB, but that is not the point. The point is that there will exist this kind of a relation which ensures the thermal equilibrium between system A and C. There will exist this kind of a functional relation which ensures the thermal equilibrium between system C and D. Okay. Now, from these two equations, what we can do, we can solve for, say for example, both these equations have y prime. So from this equation, I can solve this equation and write down my y prime is equal to some function g is c, which will be a function of x, y, and x prime. And from this, actually, I can write down my y prime is equal to some function, another function, GCB x prime, x double prime, y double prime, and x prime. Okay, so I can solve for y prime from this equation. I can also solve for y prime from this equation, and I will get these two relation. And obviously, since y prime is equal to this, and also y prime is equal to this at equilibrium, so obviously I can write down another interesting relation, which is g of AC should be equal to g of CB x double prime, y double prime, and x prime. So till now we have not used the notion of zero law of thermodynamics, right? We have not used the idea of zero law of thermodynamics. We used the idea that A and C are in equilibrium. We have used the idea that C and B are in equilibrium. So that gives me this relation, A and C equilibrium. CB equilibrium will give me this relation. I just solve this and obtain this relation. Zero law of thermodynamics have not been used yet. There is no use. what zero law of thermodynamics tells you. So A is in thermal equilibrium with C, B is in thermal equilibrium with C. So zeroth law of thermodynamics tells you that A and B are in thermal equilibrium with each other, right? So that will give you another this kind of relation. So I can write down from zeroth law of thermodynamics. I can write down another this kind of relation which will be f of AB. This part of board is visible, right? Yes or no?
Yes, sir.
Yes, sir.
Okay, so f of AB, this will be a function of x, y, x double prime, y double prime is equal to 0. It is important to note that the exact functional form of FAC, FCD, and FAB they may be completely different, but that is not the point. The point is there exists a functional form like that. Okay, so this is zeroth law of thermodynamics. Tells you that there should exist a relation like this. Okay, now look at this equation and this equation, these two equations. They are essentially telling the same thing. They are essentially telling that the system A and system B are in thermal equilibrium. But this equation has an extra coordinate x prime, which is not related to system A or system B. This x prime coordinate is related to system C, right? So since this equation tells you about the thermal equilibrium between the system A and system B, there is nothing to do with the system C. So this x prime should be dropped. I mean, the functional form of this GAC and GCP should be such that you should be able to eliminate this x prime from this relation. If you eliminate x prime from this relation, you obtain this interesting relation. From here, from this relation, if you eliminate x prime, and together with this relation and this relation tells you that x prime should not be there in this relation. So if you eliminate x prime from this relation, you find the relation of this form. Some function h for system A some function h for system A, which is a function of x and y, should be equal to some function of h of b for system B, which is a function of x double prime and y double prime. So you all agree with this, right? You will be able to find out this kind of a relation by eliminating x prime from this relation. This is suggested by this relation that this particular relation should not depend on x prime. And similarly, you can do this analysis. You can do this. I mean, you start from this one and do this analysis. You will find that there will exist another function, which is the function HC, which will be a function of x prime and y prime, which is same as this HA and HB. At xy and x prime, x double prime, y double prime, respectively. So when these three systems are in thermal equilibrium, there exists a function of these macroscopic variables x and y or thermodynamic variables x and y, which are same for these three. I mean, for all these three systems. Okay, so the idea is that when three systems A, B, C are in thermal contact with each other, they are in thermal equilibrium. There exists a function. The system A, B, C are determined, the macroscopic description of these systems are determined variables x, y, x prime, y prime, and x double prime, y double prime. So there exists a function for A, which is HA. There exists a function for system B, which is HB, and there exists a function for system C, which is HC. They are same. The value of this function are same when the systems A, B, C are in thermal equilibrium. The value of this function is called T, the empirical temperature. Okay, so let us recapitulate the idea of temperature again. So, what zeroth law of thermodynamics tells you? Zeroth law of thermodynamics tells you that if two systems are in thermal equilibrium with the third, then the two systems are in thermal equilibrium with one another. The example is if system A and B are in thermal equilibrium with system C, then system A and B are thermal equilibrium with each other. So that means that whenever we are saying that system A and B are thermal equilibrium with the system C, there is something, some properties of these three systems are same. So you do not yet know what is that property. So that property is temperature. And from this analysis, we can say that the temperature is basically given by some function of the generalized of the thermodynamic coordinates that describes the system.
Sir,
Yeah.
sir, so then
Yes.
temperature is not defined as an independent quantity. Right?
Wait. I cannot hear you. Wait 1 second. I need to switch up something. Yes, tell me.
Well, then, like when we initially define temperature, then it's not an independent quantity. It is dependent on the thermodynamic coordinates. Like this definition, it's dependent on the thermodynamic coordinates of each system A, B, and C. Like the function.
The functional form, yes. I mean, temperature is independent. Temperature is universally defined. We will come to that. We will come to how we can have a universal definition for temperature. But for example, so what I am saying. So let us assume that this system A, this is a system of gas. Okay. So you know that for gas actually you know that PV equal to energy. So this is the equation of state. So this HA will be PV divided by multiplied by some constant.
Yeah.
Right? So if I take a system, say for example, let us assume that the system B is not a system of gas, it's a system of liquid. Okay, so then this T will be some other function of, for liquid that you need to know its volume and its density, this kind of things, its composition, etc. So then T will be some other function of this coordinate. Coordinate variables of system B. Yes.
This H is system dependent. That's for sure. Like this H is system dependent.
This functional form is system dependent. Yes.
System dependent.
Yes.
But like generally when we talk about temperature, we define a relative scale. Like based on some known value, we can
I'll
compare.
come to that. That is the next part of the lecture. Okay, I'll come to that. How to define a universal scale for temperature, I'll come to that. So this is the idea of temperature. Whenever few systems are in thermal equilibrium with one another, there are some properties that remain same for all these systems who are in thermal equilibrium. That actually argued from the zeroth law of thermodynamics, and that property is called temperature. You can have this kind of a relation.
Thank you, sir.
Okay. I will come to that universal definition, how we can universally define temperature. This is just at a level of conception. What is temperature? How we can define temperature? Okay. Let us, in this example, let us do one more thing. Let us make our conception little more clear. Okay, so let us assume that I have two systems A and a system B who are in thermal contact. The system A is specified by thermodynamic coordinate x and y, and the system B is specified by thermodynamic coordinate x prime and y prime. They are in thermal contact. Okay, they are in thermal equilibrium. So if I draw plot for system A, x and y on a plane, let us assume that this given value of x and y, let us assume that this is x0 and this is y0. This is x prime 0 at the initial condition. It is x prime 0 and y prime 0. This represent a point here. So this is my x0 and y0 here. So this is system A. Okay. Now what I do, I remove the system A from here. I remove it from here and change my x0 and y0 coordinate. So remove the system A from here, change this x0 and y0 coordinate to some x1 and y1 coordinate. So this x0, y0 could be volume, could be temperature. I mean, for ideal gas, you can think that this x0 is the volume and y0 is the pressure. Okay, so I took this system A away and then change the value x0, y0 to x1, y1 in such a way that this system A at coordinate x1 and y1 it is determined by the thermodynamic coordinate x1 and y1 and still in thermal equilibrium with the system B. So this is the way I change this coordinate in such a way that the system A is still in thermal equilibrium with system B. So let us assume that this is a point here. Similarly, I take away the system A again and change the coordinate to x2 and y2 in such a way that this system A with coordinate x2 and y2 is still in thermal equilibrium with system B. So let us assume that this is my coordinate x2 and y2. So you understand what I am doing. I have two systems A and B in thermal contact, they are in thermal equilibrium. I took away one particular system, change its coordinate, change its thermodynamic coordinate x0, y0 to x1, y1 in such a way that the system A is still in thermal equilibrium with the system B. Okay, so this is the coordinate, and I can change it in such a way that another change so that the x2, y2 system A with coordinate x2, y2 is in thermal equilibrium with system B with coordinate x0 prime and y0 prime. So all these three states x0, y0, x1, y1 and x2, y2 are in thermal equilibrium with the system B with state x0 prime and y0 prime. Three states of system A are in thermal equilibrium with another system. So what I can say that all these three states x0, y0, x1, y1 and x2, y2 are in thermal equilibrium with each other. Okay, clear, right? Since all these three states are in thermal equilibrium with this state, then these three states are in thermal equilibrium with each other. So x0, y0, x1, y1, x2, y2 are in thermal equilibrium with each other. So the line on which these states fall, the states which are thermal equilibrium with one another falls, is called isotherm. So see the consequences of zero Log thermodynamics. We can say that this x0, y0, x1, y1 and x2, y2 are in thermal equilibrium because of the consequence of zeroth law of thermodynamics. Because we know that this state is thermal equilibrium with this one, this state is also thermal equilibrium with this one, and this state is also thermal equilibrium with this one. So this is what is called the zeroth law of, in consequence of zeroth law of thermodynamics, and this line is called isotherm. Similarly, I can plot isotherm instead of moving the system A away. I can fix the system A here and move the system B away and change this coordinate. I will obtain an isotherm for system B. So I will obtain a similar, and this will be some coordinate x0 prime, x y0 prime. This may be x1 prime, y1 prime, x2 prime, y2 prime. So you understand what is the isotherm, right? So this is one particular isotherm on which isotherm is a line on which each state on each point on this line will specify a particular thermodynamic state for a given system. Isotherm is the line on which each state is in thermal equilibrium with one another. Similarly, this is the isotherm for B. If I start from a different initial condition, different initial state, I will get another isotherm. Like this, for B also I will get different isotherms. But what I can say is that all the points on this line, all the points means all the states that are specified by a points on this line will be in thermal equilibrium with all the states that are specified on a point on this line for system B. Okay, so this line is in thermal equilibrium with this line. That means each point on this line is a particular state for system A. Each point on this line is a particular state for the system B. So, if I take a particular state, particular point here, that will correspond to a particular state for system B. If I take a particular point here, that will correspond to a particular state for the system A. What I can say that these 2 points are in thermal equilibrium with one another. Okay? So there is some property of this line is common as some property of this line. So what is that common thing? That common thing is the temperature. And you are looking at that equation, those equations are basically the equations of this line. Okay? Do you understand that? For A, this line corresponds to HA equal to some constant. This each line corresponds to a given value of this T. Say T0. Say this is correspond. Say this isotherm corresponds to the empirical temperature T0, T1, T2. Okay, so if I fix that T0 is equal to HA, T0 is a given number, is a constant number. Then HA function of x and y is equal to some constant number. So that will correspond to a line on xy plane. Okay, so this is that line. Similarly, it tells you that for system B, this should be equal to HB times x double prime and y double prime. So I have based the convention, so this should be prime. Let us take the convention. So now B is my prime, not double prime. So HB equal to constant, that is the functional line, that is this line. That function corresponds to this line. If I take another different temperature, if I take instead of T0, T0 is a constant empirical temperature. If I take another temperature T1, that will give you another isotherm. For example, this isotherm and this isotherm. So my point is all this is a consequence of zeroth law of thermodynamics that tells you that when few systems are in thermal equilibrium with one another, there are some property which remains fixed for that system, and that property is the temperature. Now, our objective will be to understand what is, I mean, how we can have a universal definition for temperature. How we can, I mean, of course, we know that temperature tells you whether the system is hot or the system is cold. That actually that will be parameterized by temperatures. The parameter that tells you whether the system is hotter or colder is temperature. But we need some what to say, some globally accepted definition to scale the temperature, to have a scale for temperature and to measure how to quantify these things. So that we will do in the next session. So anyone have any questions or confusions? Anyone any questions or confusions?
So is it necessary that the system would always be defined by two thermodynamic properties?
No, no,
Why
no.
are we not considered?
No. I mean, it could be many. So I am taking the simpler system, okay? So which is defined, which can be defined by two thermodynamic variables.
Mhm.
So it is not always possible. I mean, because I took this analogy because I mean we have the analogy of ideal gas system
Uh-huh.
that can be defined by two thermodynamic properties. But there are other systems. I mean, instead of assuming a homogeneous gas, if you consider a heterogeneous gas where there are different components,
Then again, yeah, composition comes in.
another thermodynamic variables, which is the composition of the gas.
Mhm.
Okay, so this is not necessary that the system is always defined by two thermodynamic variables.
Mhm. Thank you, sir.
Any other question? Okay, so if not, let us meet after. Okay, so let us meet after 45 minutes. Okay, because today there is a conference going on and there is an interesting talk now. So I want to listen to that talk. Let us meet after 45 minutes at 11. So this is 11:30. Let us meet at 12:15. Okay. Okay. So we'll start next session at 12:15, not 12. 45 minutes break.
Thank you, sir.